All right, now you'll notice that this is going to come out of chapter 3. I don't know why it is in chapter 3. It should be in chapter 1 with the rest of the limits. We're going to talk about limits that are infinity. Okay, so Friday we talked about limits, Friday we talked about limits that were infinity or negative infinity. Today we're going to talk about limits towards infinity and negative infinity. Okay, gotta get those two straight. Okay, so the first thing we need to talk about before we can even talk about limits are horizontal asymptotes. Okay, horizontal asymptotes describe the behavior towards infinity or towards negative infinity. Probably going to be important when we're talking about limits in that direction. Okay, now, some of you might be thinking, oh, I know there are rules to horizontal asymptotes and I'm not remembering them off the top of my head right now. We're going to go over those pretty soon, so don't worry, okay? But horizontal asymptotes will be important in rational functions when we're thinking about our limits here, okay? Now, there's two types of functions we're going to primarily focus on today. Rational functions, obviously, is going to be ones we're going to focus on, but we're also going to talk about polynomials as well. All right? So, when we talk about limits at infinity, okay, we are talking about the end behavior to a function. If I'm talking about the limit as x approaches negative infinity, we're talking about what is happening as we continue to go left with the domain. We're talking about a limit towards positive infinity. What is happening to our graph as we approach the right side towards infinity? As you can see, both the right and the left end behaviors approach that asymptote of 3. Okay, so if we know where that asymptote is, that helps us get that limit. Okay, we'll talk about that. But essentially, we're just describing the left behavior and the right behavior of the graph. And we're talking about infinite limits. Limits at infinity, excuse me. Okay, so we're going to start off easy here. We're going to start with polynomials. Polynomials are the nicest types of functions, right? They're always continuous. We have all these strategies for finding zeros, which we're doing right now in pre-calc, so you don't have to worry about it anymore. Okay? They're also going to be nice when we get to Unit 2. All right? So let's give ourselves some reminders about polynomials. We have something called the leading coefficient test. Okay, let's talk about what that leading coefficient test tells us. If we have a positive leading coefficient, What does that tell us about the behavior of our polynomial? How about this? It is Tuesday after a 3-day weekend. I'm going to give you 30 seconds to discuss whatever you can remember about the leading coefficient test. With your pot, go.
Oh, yeah, yeah. So the difference is yeah. Yeah, but the other one is
I am appreciating the hand gesture.
I don't know how else to describe it.
Right, right. Okay. That's how I feel up here. You see my hands going all over the place. Okay? My family makes fun of me because I talk with my hands, but I don't care. All right? So pod 2, positive leading coefficient versus negative leading coefficient. What does it tell us?
It's the right behaviors up or down.
Okay, I like that you specified. So the right behavior is what it's telling us. Okay, so if it's a positive leading coefficient, the right is going to, okay, the right will rise, and if it is negative, the right will fall. Okay, now, then we also have to talk about odd degree versus even degree. Pod 4, what's the difference between an odd degree function and an even degree function?
If it's an odd degree, one side will be going up and one side will be going down. If it's even, both sides will be going up or both sides will be going down.
Okay, good. An odd degree will have opposite ending behaviors, while an even degree will have the same ending behaviors. Okay? I want you to think about the leading coefficient test when I give you a polynomial and I'm asking you for a limit towards infinity or negative infinity. If I'm asking you for a limit towards infinity, I'm asking you what is happening on the right side of your polynomial. If I'm asking you for a limit towards negative infinity, what's happening on the left? Okay? Okay? All right. So, let's start with this right here. The limit as x approaches positive infinity of 2x to the 5th, and the limit as x approaches negative infinity of 2x to the 5th. I wish I could do like 2 screen shades at once, but I can't. I have to hide what's right here. All right. Is it down there? Maybe I'll just do this. And then just ignore this for now. All right. So, what is happening towards the right side of our graph, Henry? The right side is rising, so our limit towards infinity is infinity. Okay. The left side of our graph, Eric, what's it doing? Okay. The left side is falling, so we're approaching negative infinity. Okay. Positive leading coefficient, the right will rise. Odd degree, the left has to do the opposite. All right, next one. 5x to the 6th. We're going to look at limits towards infinity and negative infinity. Actually, what's happening to the right side of our graph?
It rises.
it rises. So the limit towards positive infinity is infinity, because as we continue to go to the right, we have our graph is rising. Okay, as we go to the left, the limit as x approaches negative infinity. Jesus, what's happening on the left?
It's
Heading towards infinity. It's also rising. All right, good. Negative 7x to the fourth is my last polynomial that we'll look at from both directions. As we are going to the right, what is happening on our graph, Trevor? False. And as we go to the left, Will? Good. Leading coefficient's negative, so the right side's going to fall. Even degree, so that's going to be the same. All right. I'm going to give you two polynomials that I want you to look at and then compare your answers to your pod. I'm going to give you about 60 seconds to do it on your own and talk about it as a pod. Amy, what did your pod decide on for the first one?
I just from the right and then also from the left.
Okay, so if this is the limit as x approaches infinity, your answer would be?
As x approaches infinity, then positive infinity.
Positive infinity, because it rises on the right. Okay, do you agree with pod 5? Excellent. The next one, the limit as x approaches negative infinity of this lovely function. Chris, what does your pod say? And why is that? Your pod mates help you out with why you chose negative infinity.
The right-hand behavior is the positive infinity because 17 is a positive number, and then since it's an even or an odd numbered exponent, then it stops at the left side.
I like your thought process. Jenna, you see something?
Well, because it's not the highest C.
Okay, so I tricked you. Like this was kind of,
That's a low blow.
I know. So it's kind of mean, but I need you to be able to pay attention, right? Technically, that is the first term in the polynomial. Okay? We have a leading coefficient that is negative and an even degree. So both left and right behaviors are falling. So you kind of got lucky there, right? But let's make sure we have the right explanation for it, okay? Sorry to take on you guys, but I am glad you made that mistake so we could have that conversation, okay? I know they were not the only ones to be tricked either, okay? So just make sure you're paying attention. All right, now, here we go. This is kind of exciting. All right. What I'm going to let you do is write it down, because if I try to talk and you write, then it doesn't always sink in. All right. So you write, we'll talk about it, and we'll do some examples that will make more sense. What this is saying, if you have a constant over a polynomial, and we look at a limit towards infinity, what's happening with your fraction? If you have a number in the numerator and your fraction, your denominator keeps getting bigger and bigger and bigger and bigger and bigger, that fraction is going to get really close to what? 0. Okay, the bigger your denominator gets, the smaller your fraction becomes. Okay, to the point where we are approaching 0. So some constant over a polynomial, we're going at a limit towards either infinity. That fraction is going to get so small that it will approach 0, because your denominator is getting so big. Okay? So what does that look like? Here's our first example. The limit as x approaches infinity of 5 minus 2 over x squared. Now, you can separate these out in your head, or you can separate them out on paper, all right? You should think of this as the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Some of you are going to think about that in your head. Some of you are going to actually write it down. It does not bother me if you do not write this down, okay? But the limit towards, it doesn't matter if any constant, will always be that constant. Okay? The limit as x approaches infinity, we have a number over a polynomial. All right? So what's going to happen as we go towards infinity? This fraction is going to approach 0. So the limit is 5. Okay. So keep an eye out for that. If you're going towards infinity with your limit and you have a number over a polynomial, automatically it's going to go to 0. Now, what happens if you have polynomial over polynomial? Okay. This is where we have to be a little bit more analytical. Okay. If we thought about those two polynomials individually, 2x minus 1 towards the right would go to infinity. X plus 1 towards the right would go to infinity. Infinity over infinity is another one of those indeterminate forms, because infinity is not a value. We can't divide infinity by infinity. All right? So we have to have different strategies. We can't find this limit, we just have to have a different strategy. Okay? So I'm going to show you this strategy, and then we're going to talk about a different way. Okay? So the strategy that I have, if you have an infinite limit, or excuse me, a limit towards infinity of a rational function, you can divide every term by the highest degree in your denominator. Okay, what do I mean by that? In this example, the degree of the denominator is 1. So we're going to divide every term by x to the first power. Every single term. Okay? If we had a degree of 2 in the denominator, then everything would be divided by x squared. Okay? 2x over x reduces down to 2. And x over x reduces down to 1. Now, if we look at these individually, what is the limit as x approaches infinity of 1 over x? Say it louder. 0. What is the limit as x approaches infinity of 1 over x? 0. So we are left with 2 over 1. Okay? Now, that took a little bit of work, right? You could have actually done this problem without knowing anything about limits, because you know information about horizontal asymptotes, right? Let's remember our horizontal asymptote rules. Okay? When the degree in the numerator is the same as the degree in the denominator, someone please tell me, where do we find our horizontal asymptote? Eric.
The coefficient of the first term on the numerator divided by the coefficient of the first term on the denominator.
All right, we look at our coefficients. All right, here our horizontal asymptote is at 3 divided by 6, which means as we approach infinity, our graph is going to approach our horizontal asymptote of 1/2. We know that's our ending behavior. I'm going to skip down to the third one. Please write this third one down. We're going to go out of order. Somebody, please tell me our horizontal asymptote rule when the denominator has a higher degree. It is not y equals x. It's going to be y equals a number. 0. Y equals 0. Okay, I think that's where you're trying to go. Okay, so when our denominator has a larger degree, our horizontal asymptote is y equals 0. That is what our graph is going to approach as we go towards infinity. So our limit would be approaching that horizontal asymptote of 0. Okay? Now, I'm not writing down these horizontal asymptote rules because this is year number 3 of you knowing them. If you need to make notes to yourself, you do that in your notes. Okay. This one. Back up to the second one. what kind of asymptote do we get when the denominator is larger than the numerator's degree? Or excuse me, the numerator has a larger degree. We have a slant asymptote, okay? So we know that in this case, we're going to have unbounded behavior of some kind, but we're going to need to be able to figure it out. So we're going to have to use the strategy that we used on the previous slide for these ones that have slant asymptotes, okay? So what's the highest degree here in the denominator? X to the first, so we are going to have to divide everything by x to the first. Okay. I don't know why I made that negative. I'm really sorry. Okay. So we know since we're approaching negative infinity, constant over a polynomial, those are both going to go to 0. In the denominator, we have 1. Okay. Now, let's talk about 2x. What is its behavior towards negative infinity? Is it rising or falling? It is falling. It's a line that looks like this, right? To the left, we are going to be falling. So this has a limit of negative infinity. Brewing.
If x over x is negative infinity over negative infinity,
Well, algebraically, x divided by x reduces down to 1. You want to reduce before you use the substitution. Does that make sense? Kind of like how we cross out like x minus 2 over x minus 2. Okay? That's a good question. All right. 2 more examples. This is where it gets exciting. Okay. Please write this one. Okay, this looks kind of crazy, right? Since there is a radical in the denominator, it is not as cut and dry as the rationals that we had on that previous slide. Okay? We are going to look at this limit towards infinity and negative infinity, and then I'll talk to you a little bit about what's happening because of that radical. Okay? So let's go ahead and stick with our strategy that we used over here, dividing every term by the highest degree of the denominator. Technically, what is the highest degree in our denominator? I hear mumbles. What? I see an x squared. But technically, x to the first is the highest degree because x squared is underneath a radical, right? Now, we are talking about the square root of x squared, right? Which equals x as long as x is greater than 0, okay? And we're going towards infinity, so x is greater than 0. We're going to be fine. So what we're going to do is we're going to divide every term by x. 3x over x, 2 over x. Now, under the radical, x is the same thing as x squared. So when we divide by x, under the radical, it's going to look like x squared. Okay. Now, we're not changing the value of our fraction because we've done the same thing to numerator and denominator. So it's like we multiplied by 1, right? So we didn't change the value. let's go ahead and algebraically simplify here. So 3x over x is 3. 2x squared over x squared is 2. Okay. Now we can look at the limit towards infinity of each term in the numerator and denominator. If we're talking about the limit towards infinity of 2 over x, that is going to go to 0. How about 1 over x squared? All right. So what we're left with is 3 over radical 2. Okay. Now, I told you a little different when you do it this time, right? Now we're going to go towards negative infinity. Okay, same problem, yes. Well, we know that x squared, the square root of x squared equals x when x is greater than 0. What happens, what's true about the square root of x squared when x is less than 0? It wouldn't equal ix. What happens if we have square root of x squared? These cancel, right? It's the same thing as negative x. So, when we do our dividing by the highest term, okay? If underneath the radical we are dividing by x squared, but our x's are going towards the negative, right? Then that means in our numerator we have to divide by negative x because of this right here. Okay. So the only thing that's going to change we're going to get the same work, except what happens to our limit? It's negative. Okay? When we have an even radical appearing in a rational function, we get two different horizontal asymptotes. One for the right end behavior, one for the left end behavior. Okay? There's 2 minutes before the bell rings. Probably not enough time to like grab your calculator and punch it in, unless it's literally sitting in front of you. But if you want to look at what this graph looks like, I think that would be a good idea for you to understand how there are two different horizontal asymptotes, but that is happening because of that even root in the denominator. Okay? Your homework is on your gold sheets. I expect you all to do it tomorrow so that we can have a productive day of preparing for a quiz.
When we get solutions like that, do you not want them rationalized?
I do not want them rationalized because it doesn't matter in AP calculus. You can see them unrationalized. Okay? Now, if you rationalize it, I'm not going to be upset, but basically you don't have to simplify your answer in AP calculus. Okay? We have more important things to worry about.